Okay, now that we have found out the formulations to analyze in 2D stress, we're going to go ahead and analyze in 2D stress using the direct stiffness method. So at first, let me just take my pen as usual, and let's see what it says. It says, let's assume the global stiffness matrix and write the global load vector of the truss shown below. Also write the boundary conditions. Okay, so here EA by L is constant, which is 500 kPa. So here EA by L is actually the axial stiffness, and we are going to call that SX, just like previously. So EA by L is equal to actually SX. And you can see here in the formulations, here is the SX, right? And here the SX is given the value of 500. Okay, so that's out of the way. Now let's talk about something else that we require before we move on. What we need to know is the displacement. So the displacements are going to happen at the joint. So let's see how many joints this truss has. It has 1, 2, 3, and 4 joints, and here we can see that it has 5 members: 1 member, 2 member, 3 member, 4 member, and 5 members. Okay, and here are the joints: 1 joint, 2 joint, 3 joint, and 4 joint. So there are 4 joints and 5 members. Okay, so from the sign convention that we had talked about previously, what we're going to do is we're going to consider the horizontal deflection to be positive, meaning that is going to be on the right side, and we're going to consider the vertical deflection to be positive as well, so that is going to be on the upward side. Okay, all right, so that's out of the way too. Right after that, we're going to see where the displacements will occur. The displacements are going to occur at the joints. So we have 4 joints, so there are going to be 4 multiplied by 2, 8 displacements. So these are the displacements here in this figure. They are named accordingly. Okay, so A is the first joint, that is why the horizontal displacement is being called U1, the vertical displacement is being U2, second point being the B point, it is U3, U4, and then the third point being the C point, U5, U6, and the fourth point being the D point, we have U7 and U8. And remember that always the horizontal displacement is the first displacement and the vertical displacement is the second displacement, because that is how we formulated the metrics. Remember, 1, 2, 3, 4, where 1 was the horizontal displacement, 2 was the vertical displacement, 3 was the horizontal displacement, and 4 was the vertical displacement. Remember that? We have done that from the local axis matrix formulation, right? So that is how we have to calculate things. Okay, another thing that we need to know right now is the bearing angles and how to consider the bearing angles. For example, when I am developing a stiffness matrix for, let's say, this member. So this member, this is the AB member. So am I going to call that the AB member and conduct calculations like that, or am I going to call that BA member? That actually depends on the angle, the bearing angle. So whichever member call is going to give us the lesser angle value, we're going to use that member call, because we are trying to make our job simpler, not harder, right? Okay, so if we did bearing angles, let's say if we did bearing angles right over here, there you go. If we consider the member to be AB, then the bearing angle here is 0 degrees. And if we consider the member to be BA, then the bearing angle actually becomes 180 degrees. Okay, so that is why we're going to consider the member to be AB. Okay, so that is what is being done here. Alright, so here you can see that for AB, the theta value was actually 0 degrees. That is why cos theta is equals to 1 and sin theta is equals to 0. Then we're going to use this formula that we have seen previously. We're going to put in the value of C and S, cos theta and sin theta, inside this formulation, and that is how we're going to get KABG Okay, so this is where we're getting the stiffness matrix of member AB in the global axis. So here 500 is SX, right? This is SX, and these are the values that are put in here to get this result. So right over here, here's 1 is actually the short form for U1. So U1 is having the number 1, that is why we have given the number 1 here. And then U2, which was the vertical displacement, and A is being called U2, so this is the value 2. Similarly, we have 1 and 2. These are the numbers that are going to be of huge help when we're going to formulate the metrics for the entire truss instead of just a single member. Okay, so that member AB is out of the way. Let's go to member BC and see the bearing angle. So B and C, the bearing angle starts here. So this is also 0 degrees, meaning C is equal to 1, S is equal to 0. But this time it is not 1, 2, 3, 4. This is 3, 4, 5, 6 because it starts with 3. Then we have 4, then we have 5, then we have 6. So as we have said, first the horizontal displacement, which is U3 here. So this is 3, U3, horizontal displacement. Then the vertical displacement of the first point, of the first joint, not the point. And then again the horizontal displacement of the second joint. And following that, we have the vertical displacement of the second joint again. So here we have 3, 4, 5, 6, 1, 2, 3, 4 is already done. This was 1 and 2, this was 3 and 4, we have 5 and 6 here, and similarly there's going to be 7 and 8 here. Okay, so that's done. Let's so you also have the values figured out here. Okay, right after that, let's look at member BD over here. So if we do a bearing angle here, the BD is having an angle of 90 degrees. So at 90 degrees, cos theta is 0 and sin theta is 1. So this is what we are getting. This is 3, 4, and 7, 8 because here is 3, here's 4, here's 7, here's 8. Okay, so we have 3, 4, 7, 8, again 3, 4, 7, 8. That's done for BD. Now for member AD, let's take a look. If I put the bearing angle here, I'm gonna get 45 degrees here, and if I put the bearing angle here, I am getting 180 plus 45, so that's a huge angle. So we're going to call this member AD. That is why we are using member AD instead of calling it as member DA. Okay, all right, let me just erase all of this. So that's 45 degrees, so cos 45 degree and sin 45 degree. Okay, if we put those values here, then this if we put these values here in this formulation, this is what we're going to end up with. So this is 1, 2, and 7, 8 because here the horizontal displacement is 1, the vertical displacement is 2, and at here the horizontal displacement is 7 and the vertical displacement is 8. So we have 1, 2, 7, 8. Okay, moving on. If we move on here, we have only one member left, that is the CD member. If we do the DC member, if we had done a DC member, you can see the bearing angle is actually huge. But if we do the CD member, you can see the bearing angle is 135 degrees. And this is 135 degrees. Here we have 90 degrees, then we have 45 degrees, so we have 135 degrees. So at 135 degrees, cos theta is minus 1 by root 2 and sin theta is 1 by root 2. Okay, and if we place these values in this in here, then we're going to end up with this stiffness matrix right over here. Okay, that being said, so we have got the stiffness matrix for all of the individual members. Now we need to assemble them for the entire truss instead of member to member. Okay, let me just erase the mess I have made trying to point out things. Okay, there we go, it's done. Okay, moving on. So we have assembled all of these. Now we have to assemble the kg, not for a member. You can see there is no member name here because this is the stiffness matrix for the entire truss, not for a member. Here it had CD because the stiffness was for the CD member, but since this time it is just K, meaning it is for the entire truss. Okay, the entire truss. So that is where these numberings are going to come in handy for us to formulate the entire truss's stiffness matrix equation. Okay, all right. If you move on and come right over here, we can see that this is 1 and this is also 1. So let's see how many 1s we have. You can see here's 1, meaning this value is going to be counted. This is 1. Again, let's see, here we have 1, here we have 1. So this value is being counted because we have 1 and 1 here. This is 1, this is 1. 1 is to 1, this is 0.5, and we have previously here is 1. So we have 1 plus 0.5 for that place. And let's see if we have 1 here or not. No, we don't have 1 here. So this is what we have, 1 plus 0.5, as you can see right over here. Okay, if we go back, this time we're doing 2, 2. Let's see, this is 2. And this is 2. Let's not draw it like that. Let's draw it in another way so you can understand it better. Okay, so here's 2, here's 2. So this is the point that's intersecting. That means the value is 0. Again, let's look for another 2. Here we go. We have 2, and then we have 2. So this is intersecting 0.5. So we have 0 plus 0.5. Let's see if we have something else. Here we don't have 2. So we have 0 plus 0.5. We come over here, you can see it's 0 plus 0.5. Now if you go to 3, okay, so that's not actually 2, 2, that's 2, 1. I just did, sorry. It's 2, 1. This is 2, 2. We did 2, 2 right now. We didn't do 2, 1. We did 2, 2. So similarly, let's do 1, 3. So here, this is 1, this is 1, and this is 3. So we are going to get this value. Okay. Let's get that value. 1 and 3. Let's see. So we have 1 right over here, and then 3 right over here. So we have minus 1. We have minus 1. Let's see, not 1. We have 1 right over here, but we don't have any 3 in the horizontal, so this is not going to be counted. No 1s and no 3s, so we just end up with minus 1. That is why here we have minus 1. This is not the one that we calculated, we just calculated this one because we considered the column to be 1 and the row to be 3, so this is what we have calculated. Okay, let's do another one so that there are no errors. Let's do the row 4, the column 4 and the row 3. So we're going to be calculating this one, 0 plus 0 plus 0. This is what we are going to calculate now. So we are going to consider column 4 and row 3. So let's go and see where we can get this. Okay, we were doing row 3, column 4. Okay, this is column 4. This is row 3, this is the intersect, which is 0. Then again we have column 4, row 3, the intersect is 0, so 0 plus 0. Then again we have column 4, row 3, this is what it's intersecting, so plus 0. we don't have any column 4s here or row 3s here. Similarly, we don't have any column 4s or row 3s here. So here we have 0 plus 0 plus 0 for column 4 and row 3. So here in the larger matrix, here we have 0 plus 0 plus 0 for column 4 and row 3. So I hope you understand how to formulate a matrix. So you already knew how to formulate a matrix, but still I went over it. Okay, so now that we have formulated the matrix, you can see that this is a 8 by 8 matrix, which is a huge matrix, and this is going to take us a lot of calculations to solve this. So what we can do is we can apply boundary conditions, but before we apply boundary conditions, let's do the sums. Okay, so this is the summed up form right over here. Now we're going to apply the boundary conditions to discard some of the rows and the columns. So the boundary conditions are actually the support conditions. So here in the pin support, we know that the pin support is not going to allow any horizontal displacement or vertical displacement. So u1 and u2, u1 is actually 0, similar to u2, which is also 0. This is the boundary conditions. Same here for the pin support at B. This is not going to allow horizontal or vertical displacement. So here the horizontal displacement is 0, the vertical displacement is also 0. And right over here, this is a roller support. So this is going to allow the horizontal displacement, or it can allow the horizontal displacement, but it will not allow the vertical displacement. So u6 is equals to 0. Then right over here, we can see that a horizontal force is being applied, so as a vertical force is being applied here, and there is no zero force member. So this joint is actually capable of having a horizontal and a vertical displacement, but we don't know if it has any yet because we have not calculated it. Okay, so we have found the boundary conditions. u1, u2 is 0, u3, u4 is 0, and u6 is also 0. So 1, 2, 3, 4, and 6. So if we come right over here, we have 1, this is 1, 2, 3, 4, 5, 6, 7, 8. Similarly, we have 1, 2, 3, 4, 5, 6, 7, and 8. So we know that 1 is boundary conditions is 0. So this is out of the picture. We know 2 is 0. So this is out of the picture. We know 3 is 0. So 3 is out of the picture. Okay, we know 4 is 0. So 4 is out of the picture. Now 5, we don't know if it's 0 or not, so we're going to leave it at that. And 6 we know is 0, so it's out of the picture. 6, there it's out of the picture. So all else that remains is going to be used. So all else that remains is can be found right over here. So we have u5 values, which are this is u5 right over here, and then for u7 we have this, u8 we have this. So for 5, 7, 8, we have values here. We have u5, and we have u7, we have u8, we have the 0 here, we have my -20 here, we have 10 here, right? So if we assemble that, if we assemble this in a smaller matrix form, here you go, we have 1.5 minus, okay, so we have 1.5 minus 0.5, 0.5, minus 0.510, 0.502. This was the stiffness, which is here. We have u5, u7, and u8. Here are the force values. So if we solve for this, we're going to get the displacement value u5, the displacement value u7, and the displacement value u8. So here we have the displacements all figured out. Now one thing I forgot to mention right over here were actually the forces, how we assemble the forces. So we know there is a possibility of a force in the XA, the horizontal direction. Let's say a possibility of a force is here, and the possibility of another force here. Let's call this YA, let's call this XA. Okay, similarly, possibility of a force of XB and YB is also present. The possibility of a force in horizontal direction for C is not possible since it is a roller, so there is going to be only one force possibility, that is going to be YC, and XC is going to be actually 0 because there is no possibility there. So that is why we have XA, YA, YB, XB, YB, and this 0 is actually XC. Since that is a roller support, there is actually no restraint on the horizontal direction. That is why the horizontal force value is 0. Then we also have YC. Then right after that we have horizontal force. We have a horizontal force here, 20, and it is acting on the leftward side. So from our sign convention, we know that this is a negative force, and since 10 is acting on the upward sides, we know that this is a positive force. So that is what we have placed here, the negative horizontal value at D point. So this minus 20 is actually the XD value, and this positive 10 is actually the YD value. I hope this makes sense right now to you. Okay, so just like that, we have solved it. So we have gotten the displacement values here. Okay, so that is it for this video. I'll be seeing you in the next one. Thank you very much for watching.